Okay, hello. This is going to be chapter 5 on stereoisomers. I hope chapter 4 was able to help you a little bit with studying, but this is going to be about stereoisomers. And if you look at the name, stereoisomers has the word isomers in it. You've actually seen isomers before in 40A. It's constitutional isomers. It was the same chemical formula, but it was a different way of arranging them. And then you also had recently, it was conformational isomers where it was your trusty Newman projections, where it was either gauche or eclipsed or staggered or anti. Those are different ways of showing the same molecule. And this is also a different way of showing a molecule. It's the same chemical formula, but you have a different spatial arrangement. Um, these stereoisomers are non-superimposable, which means if you take both of them and then try to put them on top of each other, they cannot overlay perfectly. There's some parts that obviously stand out. So let's introduce the idea of a chiral center. A chiral center happens on carbons with 4 different substituents. So it's just any 4 different substituents. It doesn't have to be anything specific. And a physical property of these chiral carbons is that they have the ability to rotate polarized light. This isn't really important for organic chemistry, but it may end up in your upper division classes if you're a chemistry major. But if not, this is just something to keep an eye on. So let's look at these two compounds that we have here. We can first see by this first compound, we have a methyl group on the right side. We have an ethyl, and we have 2 hydrogens. And if we go back to the definition of a chiral center, it has 4 different substituents. So this molecule here is not a chiral center. But then I made it really obvious here where I switched one of the hydrogens for a bromine, but you can see how it has 4 distinct groups. It has a methyl group right here, an ethyl group right here, a bromine, and then a hydrogen right here. So this molecule has a chiral center, and it is this carbon. Okay. And because there are 4 different substituents, you do need to use 3D ways of explaining how they're oriented in space. For that, we use wedges and we use dashes. So wedges means that they're coming out of the page, or in my case, they're coming out of my tablet onto me. But dashes means they're going into the tablet. So think of it 3-dimensionally, they're going into the page or the tablet. So let's look at this example of finding the chiral center of these 3 molecules. The way a shortcut that I like to do is it's really it takes too much time to go through each carbon and check if they have 4 distinct groups. What I like to do is I just like to look for these 3D ways of showing it. They usually mean that that the carbon that they're attached to is chiral. So all we have to do is just check for that. But this is just my shortcut. If it's your first time, I would do it by each carbon, but I'll do that right now. So let's do the first carbon right here. It has 3 implicit hydrogens that are connected to it. Well, it's also connected to another C. So it's not a chiral center because this carbon is not chiral because it doesn't have 3 distinct groups. This one, it has a methyl group right here, CH3, and then another methyl group here, and then another one here. So that's also not a chiral carbon. So this molecule, we can check for this one too, but it has 2 H's here, which doesn't make it, and then this has 3. So this molecule is not chiral. This one's a little obvious, but you have a chlorine, a bromine here, and then a hydrogen with a methyl. So this is a chiral center. And then now let's look at this one. I'm just gonna focus on the ones with 3D conformations. This has a methyl group here, a hydrogen here. This is an ethyl group, right? CH2, CH3. But then it also has this methyl group here. It might look like a chiral center, but you have to remember we also had this methyl group So these are the same groups. That means this is not a chiral center. With that, we can also, if you do have a chiral center, we can define its absolute stereochemistry. So it classifies stereocenters as either R or S. It's pretty much the same way as you would saying methylhexane and then 3-methylhexane. You're making it a bit more specific. And this is Latin rooted, so sinister meaning left, and then rectus meaning right. So I'll go more in depth about that later on. But these are the rules that you would have to follow. Because it's a chiral center, it has these 4 distinct groups. And we have to assign priority to all 4 groups. We assign priority by the higher the atomic number, the higher the priority. So if I had a bromine and then if I had a methyl, the bromine would be higher than the carbon that it's attached to. So then the bromine would have higher priority. If there is a tie, there are multiple cases when there is going to be a tie. You extend it to the next atom until there is a difference. We'll get more into that later on. And then you treat alkenes and alkynes or double bonds and triple bonds as multiple individual bonds. So instead of a C to double bond it to O, if you're naming, you would treat it as a C to an O, which is the C is also bonded to another O. So sort of like that. And then once all the priorities have been assigned, once you've numbered it 1, 2, 3, 4, you would have to place the lowest priority group in the back position. If you remember, the back position means it's on the dash. Multiple cases, it's going to be an H as the lowest priority group, but that's not always the case. Usually it is. So you have to make sure, this is one of the most important rules here, where you place the lowest priority in the back. If not, try to make it in the back. I'll give you some ways of doing that, easier ways of doing that. And then once you numbered it, it'll look something like 1, 2, 3, 4, or something like that. You would go from 1 to 4. In this case, I'm going 1, 2, 3, 4 this way. And that is clockwise, so then that is considered to be R. But counterclockwise just means imagine that the 2 is now on this side. And you can see how I'm going 1, 2, 3, 4 this way. That means it's going to be an S, okay? So we'll do one here with these 3 groups that we have. Again, I'll just do my shortcut where I look at the 3D conformation. So I'm guessing that this is the chiral carbon. Let's check. It has 1, 2, 3, 4 distinct groups, which is good. Let's do priority. This carbon is directly bonded to the Cl. It's directly bonded to an H. It's directly bonded to a C and then another C, right? So Cl goes first, right, because it's the highest atomic number. And then the hydrogen would be last. So now is the hard part of, because if you go out 1 bond, it's a carbon, but if you also go out this way, that's also a carbon, right? So how do we assign priority there? We would have to extend 1 bond ahead. If we extend 1 bond ahead, it's bonded to an H. If we extend 1 bond, it's bonded to an H. That's still a tie, so we have to go again. 1 bond, that's another H, right? CH3. This also has 1 more, also a tie, but if we go 1 more, this is still an H, but this would go on to a C. So C is greater than H, so then this group here, this whole entire thing would be number 2. And then this methyl would be a 3. If we go from 1 to 2 to 3, 1, 2, 3, 4, it's going this way. And that is counterclockwise, so that would be an S. Okay. Let's do this one. Oh, and then we also have to make sure that the lowest priority is in the back, which in this case, we didn't really have to do anything because it was already in the back. So now this one, let's assign priority. Bromine is higher than chlorine in atomic number. 1, 2. The H would be the last one, and then this methyl group would be a 3, right? But notice that the hydrogen is not on a dash. It's on a wedge, which means it's forward. we want the lowest numbered group in the back, right? But since this is in the forward position, we can just flip the stereochemistry to make it like that. So I'll show you what I mean. Let's just keep doing this the exact same way that we were doing. 1 to 2 to 3 to 4 right here. So it's going counterclockwise. So it would be S if the hydrogen was on this dash. But since it's on a wedge, meaning it's forward, we can just flip this S into an R. And it'll mean that the hydrogen is now on the back here. Okay, that's a shortcut that you can use if your hydrogen is on a wedge. So even though this is going this way as an S, it would be an S stereocenter if the hydrogen was on the back position, but instead this bromine is on the back position and the hydrogen is on the front. But it doesn't matter because we can just flip the S into the R position, right? And then let's also do it for this one. Chlorine would be number 1 as well. If we extend one bond, we're at a C, and then a C. Another bond, we're at an H, we add a C, and then we have a C. So this one loses, so this is number 4. And then now comes the tricky part where we extend one bond, it's a C, it's a C. We extend another bond, that's also a C, this is also a C, but we also have this bond too. Remember, we're counting each double bond as multiple single bonds, right? So it would look like this. But then this is also connected to that C in the middle, in the end right here. But this has an H right here, but this also has an H. So we're all tied there. But if we just keep going one bond ahead over here, we're given by H's here, right? By this methyl group. And also here, we're also given by H's. And then if you go back here, you have 2 H's. But then you also have to remember this also counts as 1, going backwards of the alkene. So in this case, the alkene gets priority instead of this group right here, which is an isopropyl group. So now we do this as 2. This is 3. And then it's going this way. That is R, but our lowest group is on a wedge. So I would have to flip the R to an S. I'll put the 3 there. Okay. And then with the R's and S's, you have something called enantiomers and diastereomers. They're just another way of explaining what type of stereoisomers these molecules are. So let's quickly do the the naming for these compounds. So I'll start over here. We have a 1 here, a 2 over there, 3, and then we have an invisible H here as the 4. That is going in a clockwise. So this carbon number 2 would be an R. Let's look at carbon number 3. We have an implicit hydrogen on a wedge. This is number 1. 2 over here, 3 over here, and then 4. It's going that way. That's R, but we had to flip it, so that's S. And then let's see if it's the same thing for this one. 1, 2, 3, and then the 4 on the back. It's going that way. So that's an S, right? Because there's an implicit hydrogen here. And then this one would be 1, 2, 3, and then the hydrogen is on a wedge here. 4, going this way. That is S, but we have to flip it, so that's R. And then I want you to look at something here where I put out the carbons 2 and the carbons 3, which is this one and this one. We went from an R, an S, to an S and R. You see how we just flipped it? This is called an enantiomer. Enantiomers are stereoisomers that are mirror images and are non-superimposable. So you cannot put this on top of this one because it won't make the same compound. One thing or one substituent will always stick out. So the easiest way to know this is if you name something R and S and then it flips to S and R on the same number of carbons, then it's an enantiomer. But if we take a look at this molecule, the naming is the same. This is the same compound. So we have an R over here and an S over here. But then if this was an S going a dashed bromine, and now this is a wedged bromine, this would be an R now, right? You see how we can just flip it? And we can also check, so this is 1, this whole group is 2, methyl is 3, the implicit hydrogen is a 4. If we go this way, that's clockwise, so that's R. So we went from R to an S to R and R. You see how this one flipped, but this one stayed the same? They're called diastereomers. So they're mirror images that are superimposable. So an easy way to do this is you do the stereochemistry for one of them. You're usually given 2 compounds like this. You draw the stereochemistry for one of them. You name the stereochemistry. And at the same carbons, if they flip from R to S, then if you have an RS to a SR, then it would be an enantiomer. But if you have an RS to an RR or anything of that nature, if one of them doesn't switch, then it's a diastereomer. And then a question that might pop up is what happens if our lowest priority group is not on the front or on the back, right? So what happens if it's like right here in the plane of the carbon? So let's number these. We have the chlorine as 1. We have this ethyl group as 2, this methyl group as 3. I think it's better if I do this as 3. And then this is now 4. So if I go from 1 to 3, it's this way. So that's S, right? But that would be if the hydrogen was on the back, but now it's not on the back. And it's not on the front, so I can't flip this S to an R, okay? So what we're gonna do is we're just gonna switch things up. We want the hydrogen to be on the back, right? We want the hydrogen to be here. Now, we're just gonna switch the hydrogen with the group that's on the back. So we're gonna switch this. This is not gonna be a 3 anymore, this is gonna be a 4. We're gonna switch places with the 3, right? You see how I pretended that this hydrogen is now over here, which now I numbered it a 4. And then we're just gonna switch these two. So this becomes a 1, and then this becomes a 2. And then now we can start numbering it. So it's going this way. So that is an S stereocenter, okay? So what I did was I just switched, because I wanted this hydrogen, it was a 4, but it was not on the back or the front, so we couldn't do anything. I moved the 3 here, which was in the back, to now the plane. I moved the 4 back here. But I also did another switch where I switched the 2 position here over here, and then with the 1, okay? But you can also do it this way, where I'll draw the figure again, if this is a little bit easier for you to see. Remember that alkanes have free rotation. So this can practically move, right? So if we want this H to be on the back here, it has to move 2 bonds, right? It has to move to here and here. So we have to move everything down to 2. So the H would be here, right? And then what about this ethyl group right here? If I wanted to move 2, because I'm moving this 1, 2, everything else has to move by 2. So this ethyl here would be on this wedge. So it would be like this, CH3. The chlorine here, if we move it 2, it'd be 1, 2, it'd be on the same plane, right? And then that leaves, oh, this is an ethyl, sorry, not a methyl. CH2, CH3. And then that leaves this methyl group here, 1, 2. Now it would be where the hydrogen was. And then let's number this one, right? We have 1 here, 2 here, 3 here, 4 here. And then look at what we did. We went that way. So that is still an S. So we were correct. You can do it whichever way you want, but I think this way is a little bit easier, right? So we're just going to do a quick example here. There are 3 stereocenters here, if you can spot them. There's one over here, this one, and then this one. Feel free to do this on your own. And then there's also here, here, here. These are pretty much the same compound. So if we quickly do this, 1, 2, 3, 4, so that is R. 1, 2, 1, 2, 3, 4. That is R, but we have to flip it, so that's S. And then I'm going 1, 2, 3, 4, and then that would be an S molecule here, right? And then the same thing is going on here, so that's the same compound. So this is R, this is S, and then something happened here where it switched up. So let's do it one more time. I go up here, CC, CC. So this one wins 1, 2, 3, 4. So this is now an R. So we went from an RSS to RSR. So the name of this would be a diastereomer. Okay, I suggest you do this problem on your own if you can, and then see how I got these RSRs. But I'm just showing you now a diastereomer. And I hope this was able to help. I'll see you all in the next video.